Last time we talked about a very powerful concept called the Fourier series. It tells us that we can build up a function by adding together a bunch of sines and cosines together in just the right way that then constructs our overall function. So we talked about how we can build a function f of x, and it's got terms that account for both cosine and sine, and it's got terms that look something like this. Okay? And we talked about how we can uniquely identify the individual weights, how much of a particular cosine frequency we want to pick up to reproduce this function. There's a very nice expression that relates how a sub n can be uniquely determined. And that's due to the fact that cosines and sines are orthogonal functions. It allows us to use orthogonality to isolate a specific coefficient that corresponds to a particular frequency or mode. Now, today I'd like to do something pretty exciting, which is to apply the concepts of Fourier series to real engineering applications, in particular looking at image analysis. So pictures aren't just living in a 1D world. There is a two-dimensional world. It varies as a function of x and y. It turns out that a two-dimensional Fourier series can very easily be extended from our knowledge of a 1D Fourier series. So this is in 1D, but we could do the same thing for 2D. If we have some function that varies as a function of both x and y, a 2D world, then I'm not going to write down every coefficient, but you'd also get terms that look something like this. Just like that. So again, this is only one of the terms, but all we've done is just take another cosine that varies not only just as a function of x, but also with y. So all we need to do is to take the index, which previously was just over n, because that n told you which frequency of cosine and sines to take. Same thing over here. We're going to add to that another index, m, that runs along the y direction. So you can see the second term over here on the right, m pi y, tells you the frequency along the y direction. And now we have two different domain sizes, Lx, that tells you how big your space is along the x direction, and then Ly, how big your domain is along the y direction. Okay? And a sub nm tells you how much weight to that particular combination of x and y frequency do I want to have to reproduce my full function in 2D. Now, this 2D Fourier series has a really cool application in engineering related to image analysis. So what I've done is to create a little MATLAB code here. And what I've done is to create a bunch of waves in 1D and 2D to show you how an image can be built up from using a summation of a bunch of sines and cosines. So what I have here is I'm specifically creating a wave of sines and cosines of different frequencies, amplitudes, and orientation. So let's take a look at one of the cases. So if I evaluate this script, what I've done here is to create a 1D wave over here on the left. This is the real space plot of a 1D wave that has valleys and peaks along the x direction. So here, the bright spots indicate regions of high amplitude, and the black regions show you regions of low amplitude. So think of a mountain and valley that goes up and down, and you can see that it varies along the x direction, but along the y direction, there's no variation. It's just a constant. At every given value of x, it's constant along the y direction. So it's a wave that only varies in the x direction in 1D. So that's in real space. So now if I take this picture, which has different intensities depending on whether you're at the valley or the peak, take the Fourier transform of that picture, what you'd get is the plot on the right. So over here, what we're plotting is along the x-axis, we're plotting the index n. So up here, this index n is what's plotted over here on the bottom. Okay? So up here, we've defined the Fourier series going from n of 1 to infinity, m of 1 to infinity, so all the positive integer values of n and m. Technically, with the way numerical solvers handle Fourier series, they handle it as a two-sided Fourier series. So there's a negative infinity to positive infinity. So that's why there could be 2 points that represents what we have up here. But that's a technical detail that I don't want you to worry about so much. But the key point is that if you look down here, we have a single dot residing at the point n equal to 10. And like I said, we have a reciprocal point over here at n equal to negative 10. And the reason why is because if you go back to the real space picture, there are exactly 10 up and down waves along the x direction. You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 oscillations along your x domain. And therefore, when you take the Fourier transform of that real space picture and go over to the Fourier domain, you have one signal only at n equal to 10 and n equal to negative 10, but everywhere else along the plane, it has a value of 0 because it has no other sines and cosines. That single dot at n equal to 10 is uniquely able to reproduce this entire picture on the left-hand side. They contain the exact same information. So now let's suppose that I were to take this image and just rotate it by 90 degrees. So let's do that real quick. Now what we have here is the same image, just rotated by 90 degrees. It still oscillates 10 times. Now it oscillates along the y direction, not along the x. And therefore, when you take the Fourier transform of that image, now moving over to the right-hand plot, where we're plotting, again, the index n along the x, and then m along the y, you see a single dot at 10 and negative 10. Again, that makes sense because now all we have is a coefficient that accounts for m of 10, corresponding to 10 oscillations along the y, and no variation along the x. So you're starting to get the feeling of what this Fourier space diagram is telling us. The distance from the origin to the dot tells you the frequency in real space. So we have 10 ups and downs of the wave going along y, so this distance is exactly 10. Okay, let's add one more element to this idea. If I were to take this image, earlier we rotated it by 90 degrees, but let's suppose we rotate it only by 45 degrees. So let's do that. I'm going to go in here. I'm going to generate a new plot where now all I've done is to take the same striped pattern, rotate it so it's pointing along the negative 45 degree. So now you could see that the values are high, so the white spots correspond to large amplitude, so a value of 1. The black corresponds to negative 1, so 1, negative 1, up, down. It's literally a sine wave, and the brightness tells you the amplitude at that point in real space. So it goes up and down, up and down, up and down, and it's pointing along the negative 45 degree. So now if you go over to the corresponding Fourier space of the image, all you've done is to take those two dots that first appeared along the horizontal, along the x in the first case, and then along the vertical. All it does is it tilts it along the negative 45 degree. So you have a point here that has a tilt of 45 degrees. And you can actually find that the distance between the origin and that point is still exactly 10. Because we haven't changed the frequency of the patterns. It's still oscillation of 10, it's just tilted. So now we've added a second component to this Fourier space interpretation. So the distance from the origin to that point tells you the frequency that you see inside your image, but the tilt about your origin tells you the tilt of the orientation of your patterns in real space. So now what we can do is we can take combinations of these patterns and add them together. So let's do that. I'm going to take the first three patterns that I just explained, the waves along the x, waves along the y, waves along the negative 45, add them all together. If you do that, you get a checkered pattern that looks just like this. It's really cool already. It's starting to look like a very complicated pattern, a little bit more sophisticated than the waves that I showed you earlier. Now you can really see that there is a band along x, band along y, and maybe another pattern along the -45. It kind of looks like those optical puzzles that you look at and there's another feature hidden somewhere in between. But it's a really cool pattern. It seems very complicated when you look at the real image, but if you take the Fourier transform and bring it over to the Fourier space, it's actually no big deal. All you've done is, again, you have the points along n equal to 10. That's the horizontal wave you see along the x direction. There's still the point along m of 10. That's the vertical wave pointing along the y direction. And then you just superimposed another pair of points lying along the -45 degree. That's it. Again, this Fourier space data, this plot, contains the exact same information as this really complicated picture over on the left-hand side. Let's suppose that I just showed you, I hid the right-hand Fourier side and just showed you the real space picture. And I showed you this diagram or this figure for about 10 seconds. And I ask you, okay, please reproduce this pattern on a sheet of paper. It would be pretty hard to do. Right, it's got these waves and some points appear a little darker, but some points are a little brighter. It might be really hard for you to reproduce that. But on the other hand, if I said, okay, I'm going to hand you only the Fourier space side and said, I'm going to show you this plot for 10 seconds, can you reproduce that? Sure, yeah, of course you can. You just have 3 dots, boom, 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 flip it on the origin, that's it. So it'd be very easy for you to carry 3 numbers, right? That's all you need. If you can memorize 3 numbers and where they're located, you can actually fully reproduce the entire image in real space. So this is like a ridiculously cool concept that you can take this really high-dimensional, real space, complicated image and just break it down and pick out the key isolation features from that, which just corresponds to a couple of sines and cosines. That's it. So in terms of densification of data from a super high dimensional space over on the left and to a very, very few and dominant modes on the right, this is a perfect example of that. And in fact, this really cuts to the heart of data science and machine learning. It's about how do you take a complicated feature, densify those features into a few number of modes, and identify patterns from those modes. That's kind of data science simplified into a single sentence. Of course, it's a lot more complicated than that, but the essence, this example is a very good one. Now, let me do one more thing. So you've now seen that the distance from the origin to that point tells you the frequency of your image. And you can see that because all of these points are frequency of 10, it will just form a circle around the origin. And the tilt tells you the orientation of your wave in real space. Now, let me do one more thing. I'm going to take those patterns but add to that another curve on top of that, where now what I've done here is take the same horizontal frequency of 10, vertical frequency of 10, but just added in there a -45 wave that is twice the amplitude of the horizontal wave and the vertical wave. So what we're saying is that the waves that now fall along the -45 have an amplitude of 2 and -2, compared to an amplitude of 1 and -1 that lies along the horizontal and vertical. So those waves along the -45, same frequency, but their peaks and valleys are taller and deeper on each oscillation. And you can kind of see that in the real image. You can see that this picture, you can see that the stripes that fall along the -45 are much more pronounced. They appear brighter to you, because the amplitude of those peaks and valleys are deeper and taller. Now, if you take the Fourier series or Fourier transform of that image, what you get is still the 3 dots, because we haven't really changed anything from the previous example. But all we've done is we've made that point along the negative 45 brighter. So this is a third aspect of how to interpret the Fourier space diagram. So the brightness of these dots indicate the amplitude of a particular wave in real space. So because the amplitude of the waves that fall along the negative 45 over in this image is twice as deep, twice as tall, the brightness of that point is twice as bright as the points that fall along the y-axis and the x-axis for n and m. Horizontal wave, vertical wave. Those waves are smaller in amplitude, and therefore in the Fourier series diagram, it appears dimmer. So in summary, there's really 3 things that you need to think about when you're looking at a Fourier space diagram. First, the distance of a particular point from the origin tells you the frequency in real space. The tilt tells you the orientation in real space. And lastly, the brightness of the point in Fourier space tells you the amplitude of that wave in real space. So I'm going to show you one more example. What we've done here is to now take the same waves that I showed you, horizontal frequency of 10, vertical frequency of 10, negative 45 frequency of 10, twice the amplitude, but I've added in there another point with a frequency of 20. So you can see in the real space, there's another signal hidden in there with a higher frequency up and down, up and down. Now that wave goes up and down 20 times. So you can see over here in the Fourier space, there's another point along here, and this distance from the origin is 20. Okay, so now you're probably starting to see where we're going. You can take a complicated image like the one you see on the left. Now it's really complicated, right? I mean, if you thought just summing 2 waves is complicated, I mean, this is a summation of 4 waves now, and it's getting really complicated. It's starting to really look like a picture. But as complicated as this might look, it turns out that in the Fourier space, it's only 4 dots. I just need to memorize 4 dots, their amplitude, and their location, and I can reproduce this super complicated image over on the left-hand side. So let's summarize those 3 components to consider when looking at a Fourier space diagram. When you have a Fourier space representation of waves along the x and waves along the y, what you're plotting is the index. Which mode number? What is the frequency or mode number of the oscillations along x and y? The particular point, this distance, tells you the frequency in your real space. The tilt of those points tells you the tilt or the orientation of your waves in real space. And the brightness of your points, the brightness, let's say has a value of 2 here, has a value of 1 up there, means that this amplitude corresponding to this wave along the negative 45 is going to have an amplitude twice as big compared to the wave along your x direction. Okay, so let's write these things down. Okay, you have your real space picture, and you have your Fourier space representation of that picture. Now, you have the frequency, how many oscillations it does. I'll just say frequency, or oscillations, comes directly from the distance from the origin. That's one thing. The second thing is the orientation of your patterns. Comes from the tilt of your points in the Fourier domain. Okay? Lastly, the amplitude of the pattern inside your real space image comes from the brightness or the magnitude of your points in the Fourier space. So it turns out that you have these three components when you're looking at a Fourier space diagram. This tells you the frequency, this tells you the orientation, and this tells you the amplitude of a particular feature or pattern or a wave inside your real space image. So hopefully you're getting an idea of how Fourier series might be really useful for image analysis. Because what you are seeing from these examples of putting simple sines and cosines together is that we might just be able to build up a very complicated image from just taking more and more of these sines and cosines and adding them together in the Fourier domain. So what we have is an image, which, as you saw it earlier, could be really complicated. It could have waves along any angle, any magnitude, any frequency, any tilt. And when you take that complicated image and you bring it to the Fourier domain, all you have are just a couple of dots here and there. Okay? So as you can imagine, you can have a very complicated signal in the real space domain, but have it be really, really simple in the Fourier domain. But it turns out that both of these contain the same information. So whether you hand me your super complicated image or whether you hand me this very simple diagram with 6 points, they contain the exact same information. And I don't know about you, but I don't want to remember super complicated things. I just remember 6 numbers, where they're located, that's it. And a computer works the same way. A computer does not want to hold many, many, many memory sizes of all the features that you hand in, right? It would rather just break that down and remember 3 points or 6 points. And if that's all it takes to make something complicated, oh yeah, of course we're just going to save those 3 values and save a lot of memory inside of our brain, but also save a lot of memory inside your computer. So this is how a lot of data and a lot of functions are handled and stored. It densifies something very complicated into fewer components and fewer parts that we need to memorize. Okay, so as you can imagine, if you tried to store the information over here, it would be large. So large file sizes. Lots of things to remember about a real space image. But over here on the right, it's going to be a much smaller size because you don't have to remember as much. So with the question earlier, if I'm going to show you this picture for 10 seconds and I want you to reproduce it for me, that would be really, really hard to do over here, but much easier over here. So that's really how powerful Fourier series can be in a lot of areas of science and engineering, but images, I think, is a very good visual representation of seeing how powerful Fourier series might be. I just want to make a quick comment about densification of data and identifying patterns, because there's a lot of excitement around machine learning and data science and neural networks. Primitively, the way I think about it is whenever you have a large, high-dimensional data set that you densify and compress into the few key modes or features of that complex data and combine these two things together, that really goes to the heart of data science and machine learning and neural networks. It's about finding patterns of complicated data, but densifying it to smaller features is really one way in which we can make a lot of progress in finding how to predict phenomena, how to understand phenomena. So I feel like primitively, the Fourier transform Fourier series is a perfect example of like the core essence of taking something very complicated, like a picture. A picture is super complicated. Your eyes are looking at a very complicated reality, but it's picking out few features and we're adding meaning to it through what we see. And I think the identification of the key modes is really a very fascinating subject. And in my mind, the Fourier series is a perfect example of this. At this stage, you're starting to get an idea that we can take a complicated feature, break it down into a sum of individual sines and cosines, and even something as complicated as an image. So I'd like to end with what I think is a really cool example of using Fourier series to an actual complicated image. So what I have here is I'm going to first load a picture of an adorable little thing. Here it is. Here's Coco. Very adorable. Super, super cute. And this picture of Coco is very complicated. I mean, there are so many shapes. The contrast between black and white it's very complicated. And actually, if we zoom into this picture, it's going to zoom in. Coco is really adorable, isn't she? What you're going to find is that a picture, an image like this, is just individual pixels. So now I'm really zooming in. So now you can see here is an individual square. And that square, that's a pixel, carries some level of brightness to it. So if a square is dark, it's got a small value. And if a particular square is very bright, it's got a large value at that position in that pixel. And a picture is just a composition of many of those squares that together make patterns and shapes. So really, a picture is just a matrix, a 2D matrix of the size of the picture, with each entry in that matrix carrying a number. And for a picture like this, which is an 8-bit picture, each square can carry 2 to the 8 value. So that will be 256. So every element inside this matrix, a single pixel, will carry a value between 0 and 255 or 256, depending on where you start, if it's 0 or 1. Okay? So now if we actually go into the MATLAB workspace, so the variable b is Coco. So here is a gigantic matrix corresponding to this picture of Coco. And it has a matrix size of 3,520 rows times 1,980 columns. So you can see that every single square inside this matrix carries a value between 0 and 255 or 256, and it corresponds to a particular brightness of that picture of Coco. So for example, if I were to go down somewhere along here, and now I'm highlighting the entire row for this particular row, and if I were to plot this row, a 1D cross-section. So what I'm plotting here on the left is a 1D cross-section of probably somewhere along here. So I've taken a particular cross-section, fixed my y position, and taken a line trace along this image, along the x direction, and I'm plotting the value of those pixels that carries 0 to 255 at that position as a function of x. So the y-axis here is the intensity, how bright that point is. On the x-axis here, I'm plotting the position along the x direction. Now, and you can see the x direction has a maximum distance of 1,980, which is the number of pixels along the x direction. So now what we have here is you can see that very early on for small x, the values are pretty high. It's very close to the maximum value. It's like around 200. And so that's probably the background floor. And you can see that the background floor is pretty bright. And so it needs a lot of signal there to capture that brightness. But now as we move closer and closer to the right, boom, right there, we enter Coco's what? Is that her back? Lower back. We've entered Coco's lower back. So now what we've done is this signal immediately drops from a very large value of the floor down to a very small value of about 50, because all of a sudden we're entering Coco's body, and she happens to be a black German Shepherd, Border Collie, Lab, Poodle. I forgot what else she has, but she's black, and therefore it drops to a very small value. A black color doesn't require a lot of any color at all, so the intensity is very small. And as we keep moving over and over to the right, it still stays at a low value. There's a small increase right there, and that increase is likely due to that little reflection in the light. I can kind of see this spot. You see how this spot gets a little brighter? So it must be it. That little brightening based on the light of the room must have just made her coat very bright there. She's a young dog, so her fur is just radiating with beauty and brightness. And then it drops again because we're going deeper into her leg there, so it turns black again, so it goes to 0, right? No intensity. And then boom, we go back up to a large value because we've probably entered her stomach chest area where she has a white coat, probably from her Border Collie days. She has a white coat here, so it goes up to a large value. And then as we cross that, we just reach her left paw there, which is also black around this region, so it goes back down, and then boom, we've entered the flooring again in the background. It goes back to the background large value. So that's just a 1D cross-section of this image along the x. And now you can really start to see waves. I don't know if you can see waves. I see waves. I see sines and cosines along this plot. I see a small little cosine here that might have some mode. And I also see a very, very high frequency sine and cosine here as well. So you can really see that maybe, just maybe, if I take a bunch of sines and cosines together, add them up, I might be able to reproduce this function along x. And I could do the same thing along y. And maybe I can reproduce this entire image by just summing together a bunch of sines and cosines. And in fact, that's exactly what you can do. That's exactly how people analyze images. Okay, so you just saw that a 1D cross-section along Coco's mid-body section produced sines and cosines, and you can see the high-frequency noise and the low, lazy oscillations. So we're going to take the Fourier transform of Coco and see what we get. So now I'm going to take this guy, take the Fourier transform of the image you just saw, and what you get is this plot on the right-hand side. So we're plotting here is the same plot we've been showing for the simple toy examples of the waves I've been showing earlier, where along the x direction we're showing the modes along the x, so n, and then the modes along the y are shown here, and that's m. Okay? So earlier, of course, it was very easy as a toy example. We just had one dot at x, this mode of 10, formed a little 3 dots here and there, and that reproduced the wavy patterns. But Coco is not just a simple wavy pattern. She's a sophisticated image. And therefore, we're not going to need just one of these dots in the Fourier space, but we're going to need a collection of all of these modes. And the brightness varies as a function of position because that's what's needed to precisely capture all the geometrical features, the color patterns, the shapes that you see in this complicated image. So what's really exciting and interesting about representing an image like this is that you can start to play some really cool tricks on images. Earlier, we took a 1D cross-section of Coco right along here. What you saw is that it was composed of some high-frequency little jiggles and oscillations that you saw. That's likely due to the fact that if I were to zoom into the image, yeah, I see some high frequency waves. I see bright, dark, bright there, dark, dark, bright, dark, right? So those are single pixel oscillations. Those are high frequency. Usually could be very noisy at those high frequency oscillations. But I also see, like you saw earlier with the cross section, a very long and lazy and large amplitude sine and cosine mode. Those modes tend to be located very close to the origin, and the high frequency up and down waves end up being very far away from the origin. So now imagine this. Suppose that I wanted to compress this image. I don't want to store all the fine little single pixel details. I just want to capture Coco's overall features, the shape, the coloring, but I don't really care about getting the really fine features that you see in this image. What we can do is do exactly that over in the Fourier domain very easily. All I need to do is take all the signal out here, all the way far away from the origin, and just zero that out, right? So if I zero all those large frequency values out and zero everywhere out here, but keep a low frequency or low mode signal, just don't do anything to them, keep it as is, then what you've effectively done is to remove all the high frequency signal you see over here on the image, but retain the overall morphology and shapes and pattern of that image. So let's do that and see what happens. So what we're going to do here is this exercise of compression. What we're going to do is we're going to take the Fourier transform. I'm going to take various cutoffs beyond which I'm not going to keep the Fourier signal anymore. So these are the cutoff filters. This is called the Fourier filter. So I'm going to execute this. And so now I'm going to create 4 different cases. This case over here is the most compressed version. This picture you see right here, the center image, as you can tell, compared to the image on the left, is crisper. It's sharper. You can see the fine features of Coco much better compared to this highly pixelated compressed version on the left, right? That's pretty obvious, okay? So then if you look at the Fourier space domain, this image you see on the right, which is the Fourier space representation of the center picture, you can tell still has a lot of modes present. I've cut off all the signal out here far away from the origin, but I've retained largely the signal along the origin because those are important for capturing the basic morphology and shapes and pattern of this picture. Now, if I wanted to save even more space, then I can take a more aggressive filter. And now this filter, as you can see, I've only retained literally the key modes very close to the center, and this inversion back would create this picture over on the left-hand side. So you can see that I'm just taking different values, different cutoff distances, and zeroing out everywhere far away. So what we're doing is taking a picture, Fourier transforming that, removing the high frequency modes and zeroing that out, inverting that back into the real space, and you've created yourself a compressed image containing less data. So the benefit of this, of course, is the fact that now this image contains less memory. So here I've saved each of those images as a PNG file. So let's go back into the file and see how much I've actually saved. So here is the file location. What I have here, the first compression, which was the one that I showed you in the center, that's about a megabyte. About a megabyte of space saved as a PNG. And as I compress it more and more, now going to this lower one, so these 4 are the ones that I've compressed, the strongest compression is only about a half a megabyte. So clearly, right, the image on the left was very pixelated because I've intentionally compressed it. Now the file size is literally smaller. This is how compression works. So when you often use Adobe Illustrator or Adobe Photoshop and you go to that tab on the upper left corner and go to Images, Compress, or compress your PDF or whatever, this is kind of like the basic essence of what you are doing. You're taking an image Fourier transforming that, doing a Fourier filter, and then going back to the real space. So it might seem something very black boxy when you click on points using Adobe products, but fundamentally, the core science is just, well, I'm showing you right now, Fourier series, inversions, cutting off certain frequencies that you don't want. OK, so in summary, what we've done is you take an original image, you've Fourier transformed it, which was initially very complicated. So let's just put a lot of points in here. You had points everywhere. Okay, in fact, it fills this whole domain. It was a little bit more concentrated along the origin. It looks something like this. So this was the Fourier space version of the original image. But with the Fourier filter, what we've done is just said, oh, I don't want all of these modes all the way out here. So I'm going to erase all that. And I'm just going to retain a smaller subsection of points clustered around the origin. And then you go back into the real domain, and there you have a compressed image. So very, very easy to do, and a very cool representation or example of what Fourier series can do to an image. If I asked you to take this original image, not using any Fourier series at all, and just take that image and remove all those high frequency noise, it would be really, really hard to do. I don't know how I would do that manually in the real space. But then taking it into the Fourier domain, easy, right? Literally a couple of seconds later, you have a compressed image with the key features that you want, the overall morphology, while you remove the high frequency noise. So one last example of how we can use Fourier series to clean up an image. So suppose you had a really bad camera from back in the day, and you take a picture of Coco, and it turns out really blurry and bad and very pixelated and noisy. Suppose your picture looks something like this. I mean, this is a absolutely horrendous picture of Coco. But imagine that this was all you had, and it was very blurry. And you can tell that if I were to zoom in, terrible. I mean, the noise of this image is absolutely terrible. You can really see the black, white on a single pixel level. So the Fourier series representation of this image looks like what you see on the right. As you can see, there is signal everywhere. I mean, if I were to zoom in here, those are all values. It's saying I need all of these sines and cosines, even the ones very far away from the origin, to reproduce this blurry image. Now suppose I wanted you to clean this up. I wanted you to take this really blurry, pixelated, noisy image and clean it up for me. Remove the noise. Well, before Fourier transform Fourier series, that would seem like a very daunting thing to do. You would have to go in there and manually, oh my gosh, it's just crazy to think about. I would take that white point, make it grayer, make it black. I would go to every single pixel and then adjust every entry of that matrix. That sounds like a very, very terrible thing to do. So what we're going to do instead is to go into the Fourier domain. I'm going to do is to just remove everything outside of here. So I'm going to create a small little circle close to the origin and keep all the signal there, but zero out everything outside this circle. And now, if I recreate the image using the exact same data as the one on the left, you get a much, much cleaner image like the one you see on the right. Now you can actually see this adorable picture of Coco with all of her features, well, not all, more of her features revealed compared to the one on the left. I mean, look at this. You can't even see her collar. There's a collar here that now you can actually resolve. I mean, it's pretty incredible. The white point of her eye, away from her cornea, her sclera, you can see her eye, the white part. I mean, there's so many more features that you can uncover just by removing the noise in Fourier space. And I just wanted to extend this by saying that in science and engineering, this kind of use of the Fourier series and Fourier transform is everywhere. In my research in fluid mechanics, material science, polymer dynamics, complex fluids, we use Fourier series all the time. I mean, it's almost like a language. We almost exclusively talk in the Fourier domain sometimes because it's more helpful and more intuitive to pick up patterns in the Fourier domain compared to the real domain. So there you have it, a really cool application, what I think is a really cool and cute application of a Fourier transform in Fourier series applied to image analysis. Now you can all get a job at Adobe. Good luck.